just continue what we were doing in the previous lecture. We are now trying to understand this 8086 microprocessor from a programmer's perspective, right? So programming model is something that we have already seen in the morning lecture, and now we want to make some small programs for that. So before proceeding, let me make an important announcement. On the coming Monday, you will be having your mini test, right? And the mini test will be such that there will be 10 objective type questions. Every question will have multiple answers. I mean, it's not that for a particular question you will only be getting 4 choices. It might be that for one question you might get 10 choices. And out of those 10 choices, some of the choices will be correct, right? Some of the choices will be correct. I mean, for a particular question, if 10 options are given, 2 or 3 options out of them will be correct, and you have to mark all the correct answers, right? So that will be the format of your minor examinations, and it will be conducted in the duration of the lecture itself. So any doubts regarding your minor examination?
Sir, syllabus?
The syllabus will be the syllabus that has been covered till today. Till today, I mean, including this laboratory. Tomorrow, shall we keep one revision lecture? I mean, the next session that we have in this week, the probably day after tomorrow. Shall we keep
Yes,
some
sir.
revision and doubt clearing lecture?
Yes, sir.
Yes, sir.
Yes.
Okay, okay. So in today's lecture, so Monday, the first lecture, that is from 9 to 10, will be your mini test, and the format of the paper I have already illustrated to you. There will be 10 questions or maybe more than 10 questions depending upon what paper I will make. Every question will have multiple options. There may be more than 4 also. Every question will have multiple options, assuming that one question has got 10 choices for you to fill. It's not that only one choice will be correct. 2 or 3 choices could be correct, right? And you have to fill all the correct choices to be able to score in that particular question. So
Sir,
that way, yeah.
एक से ये तो थोड़ा सा partial marking नहीं होगी?
पार्शियल मार्किंग इसलिए नहीं होगी ना क्योंकि आपके पास ऑप्शन है व्हाट्सएप पे अपने फ्रेंड से आंसर्स पूछने के लिए. सो उसी चीज़ को अवॉइड करने के लिए ताकि आप उस क्वेश्चन को डेडिकेटेडली सॉल्व करें, हर एक ऑप्शन को अच्छे से इवेलुएट करें. यदि आपने लेक्चर्स पढ़े हुए हैं तो आई डोंट थिंक दैट यू विल टेक मोर देन 5 मिनट्स टू सॉल्व माय पेपर. बट यदि आपने नहीं पढ़ा है, in that case, you might take centuries and you won't be able to solve it. And the thing is, the options that you will get there will be different for everyone, right? So the paper might not be on Google software so that options will be fixed. I mean, for some people, some options will be visible. For some people, other options will be visible. So this communication network that has already been established between students will be completely of no use in my examinations. And this is what happens in every exam that I conduct. So minor examinations will be conducted like that. But then your mid and major examinations, they are conducted in the usual way, right? So in that also, you might have seen the papers that I have uploaded onto the files section. How many of you have seen the papers that I have uploaded onto files section for the previous year? Please raise your hands. Yeah, only few people, right? 11 people or something. That means it's not even 10% of the class. So I have already uploaded the previous year question papers, including the minor examination, onto your files folder, and you can check them for reference. The papers are very easy. For the people who have honestly read my lectures, they will be easily able to solve it because you either know it or you don't know it. That is the case. For minor examination, you don't have to solve much. So that is the case. And I will see to it if there will be some partial marking possibility, if there is a possibility of partial marking. So I will see to it. And that is how the minor examinations will happen. And the only tip that I can give you for doing the minor examination paper is don't try to communicate between yourselves or amongst yourselves, because that will not help. It's not only that it will not help, because of that your marks might be deducted, right? So I will get to know which answer has been copied from which person, because the link that I use to create my examinations is not usually the Google Forms, because in Google Forms I can't detect that, but in other softwares it can be detected. So be as honest as possible. The paper will be simple because the course is simple, right? So some basic facts about microprocessors will be asked, like for 8085, why is maybe the size of externally interfaced memory 64 kilobytes. So you will give the answer that the address bus, it is of 16 bits, that is why 2 raised to the power of 16 bits is there. So these will be present in the options, right? I mean, very simple questions will be there. You can have a look at the paper that I have posted for the last year, so you can have a look at that. So tomorrow, shall we keep a revision session, or should we continue with the programming? Not tomorrow, I mean day after tomorrow, you have a session with me. So
Revisions.
revision means it will be a doubt clearance session, because if you ask me to give you the revision for entire lectures that I have taught you up to now, 1 hour will be not very sufficient. So I will expect that you will bring some doubts and we will solve those doubts, right? Or we can also do one thing, that the previous year question paper that I have floated, we can discuss that paper.
So next lecture might be a holiday. It's Muharram.
Friday, yeah. So do we have a holiday? Yeah, Friday is Muharram. So is the day fixed? I mean, usually it is decided. I think, I am not aware, but I think that it is decided by seeing the position of moon, etc. So is it on Friday, or there is still an ambiguity that it will happen on the other day? Is anyone aware of that? Because I have not seen the academic calendar. Okay, so let me check the academic calendar here itself.
19 को है.
19 को ही है. You are sure about that, right?
Academic calendar में 19 को है.
Academic calendar में it is on 19th.
Yes.
Okay. Yeah, I mean your session will be on 19th, so 19th would be treated as a holiday then. So we do not have a session after this. You mean to say this, right?
Yes, sir.
Okay, let me check the academic calendar here itself for more clarity. So this is your academic calendar 2021. And for NIT and IIIT, it is the same, I think. Or no, let me see your academic calendar. Academic calendar for IIIT. Oh, not an academic calendar, the list of holidays. I think I don't have your list of holidays. But you are sure that it is on 19th, right?
Yes, sir.
Wait a minute, let me check it in my own calendar. Holidays 2021, general holidays. So August 19th, yeah, it is Muharram's festival on August 19th, Thursday. So since it is there in the academic calendar, so that will be a holiday and we won't have a class next. So okay, this is the last session before your minor examinations with me. So whatever is to be discussed in today's lab session. So regarding the minor format, is everybody okay?
Yes.
Yes, sir.
Okay. So let me start today's work. So in the lecture, we had just started seeing the programming model of 8086, and we got some basic acquaintance with EMU 8086 processor. So if you do not have this software, you can contact your class representative and you can get a link from your class representative about this software. But I guess he informed me that you all have that already. So let me now open that program which we were seeing earlier. So we were seeing this program for addition of two numbers. We had seen one program already, which was this program. simple program to see the data transfer between the registers. And we emulated it by pressing this emulate button, and we saw some basic details of this processor, this assembler actually. And some important points to note there were that if you want to browse to a particular memory location, since the address, the physical or the actual address of every memory location will be of 20 bits or 5 hexadecimal digits, that cannot be used here, right? So to be able to access the memory location, you have to supply two addresses. One is the base address and another is the offset address, right? So if you want to access a memory location, say 50,001, so here you have to write 5,000, here you have to write 5,000, and here you have to write 0001. So that way you will be able to reach to this location 50,001. And if you want to edit the content of this, simply you can just click it and you can this is how you edit the content of these memory locations. And we were already aware of the register set that we have here, and the hexadecimal representation of memory location together with its decimal representation is there, so you can see it interchangeably. And let me run it again so that we run to the default settings. And we already saw that the yellow line, on whichever line of code it is, that line is the next instruction to be executed, right? So now we will explore more things. For example, I think I also told you about these flag registers. If you click on this flag, then you will be able to see the status of these flag registers. Only the useful bits of this flag register are presented here, right? So that is regarding the flag registers. If you want to see the memory, so I think there is something to see the memory also. So let me just find it in the options, not in the files tab. Debug, no. Memory. In this view section, you can go to this memory and you will be able to see memory in this format also. Here you can supply the base address and the offset address. For example, you want to go to location 50,001, so you supply here 5,000 and a location of 1 here. If you will enter, so it will show you this entire memory block. So this is 50,001, this particular position. Then this is 50,002, 50,003. The actual physical address will be displayed here, right? So you can see this complete section of memory here, or any way you were able to see this memory here if you only want to deal with few locations. So these are the two possibilities that you have. And there are various virtual devices. There are various virtual devices that you have with this microprocessor, which are attached and can be used as external peripheral. So LED you have already seen in morning. Then you have a robot also. So if you open this program, you will be able to see this robot also. This is your robot. The arrow represents the direction in which it will be moving. And through a proper program, there are various obstacles and you can move this robot anywhere into your program. This robot can be auto-programmed, right, to rotate and move anywhere. This robot is also there. Then let us see this printer. So this printer is also there. It will be printing some data. So we will see its usage when the time is due. Then simplest.com stepper motor you have already seen. My favorite one is this thermometer, because we will be doing a lot of experiments by using this thermometer. So you can see that there is a burner which is constantly increasing the temperature of this thermometer, and we can connect this thermometer device through USB or something to our microprocessor. Internally in software, it will be automatically connected through program. So we can control the switching on and switching off of this burner by using this on-off device. So this moment I have made it as off, so you can see that the temperature will slowly start to decrease, and you can connect this thermometer to our microprocessor, and you can select you can just program this particular code so that it will be appropriately on or off depending upon whatever temperature range you require. For example, you require the temperature to be between say 40 degrees centigrades and 20 degrees centigrades, you can program this particular switch through microprocessor such that it will switch on or off the burner so that your temperature remains between these two. So this is some device which we will be using frequently. Then let's see some more devices. We are virtual device. So thermometer is there. Traffic lights you have already seen in the morning. So these are the traffic. This is the traffic light simulator, and these vehicles can be controlled by that. And we also have got this VGA. So VGA I will explain to you when we will do some programs on this, right? So these are the virtual devices that are available with this particular microprocessor. And there are various other things also which we will see when the appropriate program is being made, right? So let me jump to the second program quickly and give you some work to do, because I have been speaking since morning. I have continuous lectures. So let me just explain one program and let me give some work for you to do. So this is the program, and the program is for addition of two numbers from the externally interfaced memory. So in the externally interfaced memory, there will be two numbers which will be kept. We will load those numbers from the external memory to the internal registers of the CPU. We will add those two numbers and we will store the results somewhere. This is as simple as that. But from this program, you will be able to understand various things about this microprocessor. So let us begin. The first thing is, whenever we write a program, if we want, we first want to initialize the data segment, right? Because that's where your data will come from. That's where your data will come from, right? So through these two statements, first of all, I have moved 8000H in AX. So AX is a 16-bit register. You move 8000H into that. So AX will be initialized, and then you have copied the value of AX into DS, right? So why couldn't you do it directly? Move DS, 8000H.
The segment register hold a starting address of 16 bit, and if we provide.
Yeah, so the rule is that you cannot directly initialize the segment registers by immediate data. That is the rule. So that is why you have to keep the data in some other register, and you have to initialize it by copying that value into that, right? So this is the rule. Why this rule is there? That's none of our concern as programmer. If this is the rule, programmer has to follow that rule. So with every command, I have written these comments also for your reading. So this is putting the first four hexadecimal digits at the start of data segments into the register DS indirectly, and this we cannot directly put 8000H in DS or any other segment register. So the data cannot be directly put into these segment registers. That's what I have mentioned here. Then what you will do is, once you have initialized the data segment, you are now going to extract two values from the externally interfaced memory. So in SI, you will keep the offset address. As I told you that with data segment, SI register or DI register can be used as offset. So SI register will have the offset 0004. So which location in physical address am I referring to when I put SI as 0004? Which memory location am I using?
80,004.
80,004 is the location that I am using, right? And the way to copy the data from 80,004 location into the internal registers of the memory is in line number 8. That is this particular line. Here what we are doing is we are moving a data into DL, which is written like this in big brackets SI. What will it mean is, with this SI, the corresponding segment register will be associated, that is this DS register. By using this DS and SI, the physical address will be calculated, which happens to be 80,004, and whatever data is kept at that physical address in the externally interfaced memory location, that 1 byte data will be copied into DL register. Is it understood? Is this thing understood by everyone?
Yes, sir.
Yeah. And if instead of DL, if I write here DX register, then 2-byte data will be copied in the little endian fashion starting from the location, which is denoted by this SI0004, right? So this command can load a 1-byte data or 2-byte data. It depends on the destination. If the destination is single byte, the data which is at the offset address 0004 will be loaded. Or if instead of this DL, it happens to be DX register, it will be loading 2 bytes of data. 0004 will be kept at DL and 0005 data will be kept at DH register. That is in the little endian fashion, right? So here we have only loaded 1 byte of data from location 0004, and then I have incremented this SI value to 0005. So at next location, the next data will be loaded into CH register. So after that data has been loaded into CH register and DL register, we will add DL and CH. Now here you can see that addition command has got 2 arguments, that is DL and CH. In earlier microprocessor 8085, we can only use ADD, and after that only one register was used and the default register was assumed to be A register. And with that A register, the results of calculations will also stored in A register. Here the things are different. Now DL and CH registers will be added, and whatever is the result of addition, the result will be kept in this destination register itself. So accumulator register becomes little free. It becomes little free from holding the result of everything at every possible time. Because if you keep accumulator busy, then that also improves the efficiency of your processor. So here accumulator is free for these kind of works, so that won't be stored there. Then what I will do is, in DI register, I am moving 0001, and then I am adding DI and SI, right? So what will happen is, whatever is the content of SI now, it will be 0005 because you have incremented it once. So that content of SI will be added with this 1 because you have moved 1 in DI, and DI and SI have been added and the result have been kept in DI register. So the content of this will be 0006 after the execution of this add command. And at that particular memory location, 0006 in the data segment, we are moving the data of this DL register, which happens to contain the result of addition. So I could have directly just incremented SI once again and used here SI, but just to demonstrate that DI can also be used with this DS register, I have done the calculations by using DI. Is this program code understood by everyone?
Why are you adding DI and SI, sir?
See, my plan is I will be taking the data from 0004, 0005. Those 2 bytes data will be taken and added, and they will be stored at 0006. That's my plan, right? So data I have already loaded, SI 0004, then the data is loaded into DL. I have incremented SI, so it becomes 0005. So I have taken the data from that location into CH register, and I have added those 2 data, and the result of addition is available in DI register. Now my aim is to store the result at location 0006. SI contains 0005. So I can simply increment this SI, and in place of this, I can just simply write in brackets SI comma DL. Will that be okay? If I remove these 2 lines, and here I simply write again increment SI here, and in place of DI I place SI, will that be okay with you?
Yes, sir.
But I just wanted to demonstrate that DI can also do the same thing. So instead of incrementing SI, I have kept a value of 0001 in DI register, and SI already contains 0005 by now. So I have added SI and DI. The result will be in DI. So DI will contain 0006, and through that I have copied the data from DL to that location, which is pointed to by DI. So this is just to demonstrate the usage that DI can also be used with DS register, although the same thing can also be done with SI register. Is it okay?
Yes, sir.
Yes, sir.
Okay, so So let us now emulate the code and keep some data into external memory and see the results. Okay, so this is my program on the right hand side, and this is my emulator. So where am I making my data segment? I am starting my data segment from location 8000 base address. So let me keep here 8000. So let me reach to that particular location. So I am in this location. And where am I expecting my data from? From offset address 0004 and 0005. So this is 0004. Let me keep a data of say 5 here, 05, right? And at location 0005, let me keep a data of 06 here. So what will I receive after addition?
B.
After 5 and 6, when they will be added, it will be 11 in decimal, but in hexadecimal, it will be B, right?
B.
So the data has been appropriately moved. The data has been appropriately moved here. And now what I want is, I want to just execute my program. So what will I do is, I will execute it step by step. And you can notice the changes here. So let me run this first program step by
सर ये
step and
5
slowly.
और 6 आपने जो पुट की है ये वैल्यू कैसे आ रही है?
अरे ये तो डेटा है ना, ये तो आप कुछ भी ले सकते हो. मेमोरी पे डेटा रखा है और मुझे इन दोनों को ऐड करना है.
Okay.
Right, so this is some random data. You can choose data of your choice, right? Now let me just run this program step by step. So when I will run the first step, which has been run now, a value of 8000 has been moved into AX register, and you can notice that the things which have changed in the current step are highlighted. So it is taking how many bytes inside the memory? So if you see this particular instruction, move AX 8000H. So this is a 2-byte data, and this is a 1-byte instruction. So it will be taking 3 bytes in the memory. So you can see that program, the instruction pointer has been incremented to 0003, right? So let us execute the next command so that this DS can be initialized. So now this DS contains 8000H. So now the assembler knows that you are taking the starting location of your data segment as 8000 hexadecimal, right? Now through this command, SI register will contain a value of 0004H, which it now has. Now this is an interesting command because this will load the content of 0004 offset memory location in the data segment into DL register. After the execution of this statement, what will be the value of DL register? I mean this part.
05.
05. So 05 is here. Now similarly, if you execute this move ch comma si, so this will have a value of this 06 in ch register. So you can see that 06 has appeared here. Then you will add DL and ch. The result will be stored in DL only. So you can see that 0B has appeared here. Now in DI register, we have moved a value of 01. And after that, we are adding DI and SI. So DI has got a value of 0006. Again, we will run it. So at that memory location, this data has been put and the system has been halted. So let me just check that memory location where I was expecting my result. So that memory location, the data segment begins from 5000. So let me see it from 00 itself. I will see the complete section. Okay, the system has been halted. So everything, 8000. Okay. So this is your 8000. So you can see that 5, 6 and B, they are appearing in the memory. Is it clear to everyone?
Yes, sir.
Yes.
Right. So by using this simple program, will you be able to create a Fibonacci series and store it in the data segment of this particular 8086 processor? Fibonacci series is very simple. You have to just do the operation of addition, right? The operation of addition is to be done, and then the operation of looping is also to be done, right? So looping we haven't read till now. So let me also tell you some more important programs. Okay, so let us write one simple program before that. Okay, it will be a simply addition subtraction program. So let me take one more program and then I will give you something to do. So this is a demonstration of conditional and unconditional labels, right? Program to add two numbers kept in AX and BX registers if the contents of CL are greater than 03H. If the contents of CL are greater than 03H, then AX and BX will be added. Otherwise they will be subtracted. Otherwise subtract them and add 4H, right? So what we are doing is, in AX and BX register, we have kept some data, that is 0005 and 0002. Depending upon whatever is the content in this CL register, I will keep some value. If the value of this CL register is greater than 3, then AX and BX have to be added. However, if the value in CL register is less than or equal to 3, in that particular case, the AX and BX register, they have to be subtracted, and to the result you have to add a value 04. You have to add a value 04H to the subtracted result, right? So there could be two conditions in your program, and the conditions will be determined by the content of the CL register. So let me just read out this code for you with explanation. With these two lines, you have only moved the data inside your AX and BX register. Then simply in CL register, you have put a value of 08H. Now this could be any value greater than 3, less than 3, or equal to 3. Depending upon the conditions specified in the question, the code should execute, right? So you will use this CMP command. CMP command is for comparison, and we already know how comparison command performs. It is similar to what we had in 8085. Can somebody explain what comparison command will do?
Sir, it will compare the content of CL and 03.
It will compare, but how the operation is performed?
Subtract. By subtracting both the value.
By subtracting both the values. And where will the result of subtraction be stored?
Accumulator.
Then what is the difference between subtraction and comparison command? If comparison is also doing subtraction and subtraction is doing subtraction.
Zero flag.
See, these kind of questions can be there in your examinations. The answer to this question is, subtraction command will subtract two numbers. If we talk about 8085, it will subtract two numbers and store the result in accumulator and set the appropriate flag register, right? However, comparison command in 8085, it will also perform subtraction, but it will not store the results in accumulator. It will not store the results at all. It will only set the appropriate flag bits in the flag register. Same thing happens here also. If you want to compare this CL and 03, then this subtraction will happen CL minus 03, and then the result will not be stored anywhere. Only the flag registers will be set, right? Flag registers will be set. So seeing those flag registers, you can make appropriate jump statements. Is this comparison command clear to everyone?
Yes, sir.
Now in this way, so if in 8085 we had limited number of jump instructions, jump on carry, jump on 0, but here the flag register that you have seen has more bits which are meaningful, and there are more commands because of that. So one of the command is jump on greater, JG, jump on greater to some particular label. So if the result of this subtraction, that is CL has 8 and this has 3. So if the result of this subtraction is greater than 0, JG stands for jump on greater, that is CL is greater than this number 03. So then what should happen? As per the question, what should happen?
Addition of data of AX and
Addition
BX.
of the data will happen, right? So this JG label, and wherever you are defining your label, there simply the addition will happen and the result will be stored in AX register, right? If this does not happen, I mean jump on greater to label 1 is executed as false statement, in that case, what should happen? Subtraction should happen and the result should be incremented by 4. So this subtraction will happen, subtract ax bx, and this 8 add 0004h, and then jump. This is unconditional jump to label. So this will jump to label number 2, which is halt. Because if you won't put this statement, this will also execute this addition statement. So is the program clear to everyone?
Yes, sir.
Yes, sir.
So let us run this program and see what are the results. So first two statements are simply for putting the data. So the data is already there. Then this next statement, it will put a value 8 in this CL. So 8 value has been put in CL. Now 8 is obviously greater than 3. So after this comparison operation and this jump on label operation, our code should move on to this particular line directly. Let's see if that happens or not. Yes, that has happened, and the result of addition is available in this register, right? So let me just keep a value which is less than 3. So let me keep a value of 2. So in this case, the jump should not happen, and let us run this code. So it has not jumped to that location, and it has executed accordingly. So is this clear to everyone? Yes or no?
Yes, sir.
Okay, so now write down a question. Write down a question. It is a simple Fibonacci series program, but since the structure of the externally interfaced memory is different as compared to 8085, so the question should be like this, right? So in your question, your data segment should be having the physical address of the data segment should be this. Right, so this is the physical address of the beginning of data segment. Physical address. Data segment should be this, and you have to start the Fibonacci series at offset address 0005 H. So the physical, instead of physical address, let me give you the base address. The base address of data segment is this. The offset address from where the Fibonacci series should start is 0005, and at locations 0005, at location 0005 offset, the data that is kept should be 00H, and at location 0006H, the data that is kept should be 01H. And after that, your Fibonacci series should continue. After that, your Fibonacci series should continue, and there should be a total of 20 elements in Fibonacci series, including these two locations that are already covered here. Is the problem understood clearly?
Yes, sir.
Okay, so it is 3:31 by my watch, and I give you 10 minutes to write this program. I will talk to you at 3:40. And whosoever completes the program, they can always WhatsApp it to me. I won't disclose your names because otherwise your friends will call you to copy your code. So your code will be safe, and if you send your codes to me, definitely in the lab marking there will be some effect of that. I keep the WhatsApp records forever. So whenever you complete the code, just send me a screenshot with proper comments and explanations, because ultimately that is something that you have to attach in your files also. So do it here itself and complete it within 10 minutes. So it is 3:32. Let's meet at 4:42 again. Till then, I am taking a break. You can all make that program, and we will discuss the program afterwards. Yeah, so anyone who has completed the codes? How many of you are still here? Please raise your hands. Okay, so only 31 people are here. So, are you all doing the code or just sitting idle?
Sir, I'm trying the code.
Okay. So, anyone who is nearing completion?
Done, sir.
Okay, so please share your screen and just show us what you have done. So, what's your name? Abhishek Kumar.
Abhishek, yes, sir.
Okay, wait. Yes, please share your screen and show us the code that you have made. Yes, so okay, explain the code line by line and then in the end also show us the result whether Fibonacci series is generated or not.
Yes, sir. So first of all, I moved 4000 to AX register and then copy that value into the DS segment. And the next instruction is we moved 0005 to offset address SI and then copied that value in BL. So I'm resetting all the value.
Yes, Abhishek, your voice is not audible.
Yes, sir. I'm resetting my memory and giving value 00 to 40,005 location and 01 to 40,006 location. And now I will execute one by one. Then currently my SI pointer was at 0005 and I incremented it to 0006. Then I copied the value at 0006 to BH value. And then I moved 18 to CS so that there will be total 20. First one is 0 and then 1 and then plus 18, 20. And then I created a label. In this label, I first moved the value of BH to AL register and added the value of BH and AL so that I will keep two pointer BH and AL and we'll keep incrementing all those. And then I incremented SI and kept the value of added one BH and BL1 to SI. And then again I copied back the value of BH which was previous, which was stored in AL to BL register, and then decremented the value of CX so that my loop will run 18 times. and so I decremented and then compared this value of Cx with the 0 0. If it will not be equal to 0, then it will again go to level 1 and I will execute all the instruction. If it is 0, then it will come out the loop and it will be halted.
Okay, so in your final result, let us see that series if it is generated or not.
Yes, sir. Sir, should I run in one go?
Yeah, you should run in one go only.
Yes, sir. Here is 0 0, then 0 1, then 0 1, 0 2, 0 3, 0 5, 0 8. 0 D means 13. Yeah, 13. Then like that.
Again, show me the series where it starts from 0005. Say it starts. Okay.
Yes, sir. 40,005.
So the decimal representation of the numbers is also there. 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay. Okay, so it seems correct, yeah. So any confusions in this code? Everyone else who is attempting to code it,
It's not
are you
gonna
all
give
able?
more than 14 useful members because it
What?
exceeds 255. It exceeds 255 now after 14th member of the
Yeah,
Fibonacci
yeah.
series.
That's what
So it's
I
not
am
gonna give
telling.
useful. It's
That's
not.
what I am telling that since the capability of memory is only this much, so the results after certain limit will not be correct. It will exceed the number 255. So now, can you make some arrangements to see that that does not happen? Okay, just create this Fibonacci series by using 16-bit registers now, and you can store your numbers in two locations in the memory. The same program you have to make, but this time one number, that is one 16-bit number, will be stored in how many locations? Two memory locations. Can you modify this program, all of you?
Sir, isn't 18H 24?
What?
18H is 24, right?
You check it. I mean, I can't calculate hexadecimal numbers in my mind, but you can just check it by converting it. What is your base question? I mean, are you asking this question?
Nothing important. Just
Okay, so you can just check it on hexadecimal converters or convert it for yourself. Okay, so now what you have to do is, the second program is, you have to make Fibonacci series, but the numbers should be of one word instead of one byte. So they will be stored in two consecutive memory locations. So all of you, after attempting this program, you have to just attempt the second program also. So it is 3:53 by my watch. I will see you in 10 minutes. Till then, I am here. If you have any doubts, you can ask.
Sir, should I stop sharing?
Yeah, you can stop sharing.
Okay, sir.
Okay, so Himanshu wants to share his screen. He is getting some error in his code, so he would like to see why is it not working. Himanshi, sorry. So I'm making you the presenter. After that, you can share your screen. Okay, Himanshu, you can share your screen now.
Sir, is my screen visible?
Yes, it is visible.
Sir, it is not working.
So it is getting emulated. That means technically it is correctly written. But Fibonacci series is not getting generated, right? That's what you want to say. Okay, so all of you can see this code and point out what error our friend is making.
सर जहाँ एक है सर ये 5 के ब्रैकेट में है
Please be clear, whosoever is speaking. Himanshi, your screen stopped.
Yes, sir, I have got one error. I'm trying to do it again.
Okay, okay. So rest of the people who are done with this 1 byte program, try to make it for 2 byte. One word, that is. Please raise your hands if you are attempting the second program.
Is it visible, sir?
Yeah, it is visible.
Sir, basically I have done nothing. I have same code is this, but only difference is that I am incrementing a value of aside twice whenever required, and all those value means value of the Fibonacci numbers I have been stored in AX, BX like the 16-bit register.
Okay, so result, can you just enlarge your screen and show where results are stored?
Yes. So it is in the midway, starting from 15. Here, as you can see, in line number 15 and 16, it is storing 13 and 0, and 17, 18, 21, 0, like this. And in line number 20,
Your voice is breaking, Abhishek. Yeah, tell me.
Sir, in line number 21 and 22, it stores to 33 and 0, But in 23, now it's time for 2-byte data, so it is storing in 2-byte, like 79 and 01 in decimal and respective value.
Okay, that seems correct. Acha, beyond which point the values will get incorrect?
At 12.
For this question is for everyone. For 2-byte or 1-word Fibonacci series, beyond which number will you start to get wrong results?
After 12th.
After 12?
14 to 33.
40. No. For 1 word, not 1 byte. Beyond which point the results will be incorrect for 1 byte, 1 word Fibonacci series, 16-bit Fibonacci series. Anyone? Okay, answer this question. Suppose you are creating a Fibonacci series, right? Whether it is of 1 byte or 2 byte or whatever number of bytes, and you are storing the number in externally interfaced memory, right? So by calculation, you would know that your results will become incorrect after certain duration of certain number, right? But how will the computer by itself know that this is an incorrect number for Fibonacci series or a correct number for Fibonacci series? So can you make a program? Can you make a Fibonacci series which will stop when the last correct number is stored in the memory? It will automatically stop after that. I mean, for 1 byte numbers, the Fibonacci series that you will create will be incorrect after certain number. So can you modify your first program in such a way that it will only store till the numbers which are correct, and after that it will automatically stop? Can you make this program?
The first one or the second one?
First one would be easy to do because second one has 2 bytes, so additional care has to be taken. And if you are able to do the first one, I will believe that second one will also be completed with some effort. So in first program, you need to modify it in such a way that the Fibonacci series, it will be only stored up to the last correct number that this program can calculate. So before making that program, can you just tell me what logic will you use for that?
We can compare the value with 255.
You can compare with? Shyam, you were saying something?
Most of that will not work.
See, that will do, because ultimately if the number goes out of 255 range,
so that will be negative. Same process, jump statement, jump. That will be done in
I mean, you can do that, but then again the question is, how will computer know that 255 is the number with which I have to compare it, right? So this is a program which we are making at very small scale. If suppose we have a computer which is of 64 bits or 128 bits as we have these days, so the range of the numbers there would be 2 raised to the power of 128, and that's a huge number to calculate. So how will we calculate that number on paper, because it will take entire day for calculation. So there should be a method by which computer should automatically know that now this is not getting good. So a hint is see all the flag registers that you have. So is there some flag register which change when your limit is crossed for this addition? So you can incorporate
Overflow.
that. Yeah.
Sir, can we use jump if overflow?
Overflow.
Overflow, why are you saying overflow?
Sir, auxiliary carry.
Auxiliary carry or the actual carry?
Actual
Okay,
carry.
whatever your logic is, overflow, auxiliary carry or carry, try to make a program which is automatic enough, which will display the Fibonacci series up to the best correct displayed number, right? Beyond that, it should automatically stop. So please modify your program number 1 in such a way.
Sir, yeah, it is the number 65535.
Yeah, the number has to be 65535 for one word program. And beyond that, it will be incorrect. But where do you bring this 65535 from? From your manual calculations, right? 2 raised to the power of 16 is equal to that number. So, but if you have a computer which is of say 128 bits, then what will you do? 64 bits. 2 raised to the power of 64 is to be calculated. 2 raised to the power of 128 is to be calculated. So beyond which it will display the incorrect number. But then that manual calculation will not always be possible, na? And your program will change accordingly. I mean, if you are doing the calculation for 1 byte or 2 byte or 3 bytes, so that comparison number will always change. So we want to make our program independent of that comparison number. So is there some flag, maybe overflow or carry or auxiliary carry, which can be monitored? And if the status of that changes, in that case, we can just stop our program.
We can use carry flag.
Do it. I mean, whatever logic you have, you make the program and see if it is displaying the results correctly or not. if you sum up 5000 plus this FFFF in hexadecimal, you will get the last address, right? This would be the last address. Now, you don't have to start from this last address. You have to start from last address minus 5. The fifth last address location you have to start from, and you have to start storing 5 at every location, right? So you have to create a loop based on these jump instructions, and you have to run that loop for 15 number of times. You have to run that loop for 15 number of times. Now the problem there will be that your data segment, it starts from 5000 and you are starting from the fifth last location, and you are running the loop to store 15 such memory locations, and you are filling every location with a 5 value. So now you need to verify that the segment is circular in address or not, right? So after the last location of the data segment, which is the last address that you have calculated here, this will again go to 5000H, right? So that's what you need to check. You need to verify for yourself that the addresses are circular for data segment, or for that matters for any segment. So is the problem understood?
We need to fill in reverse order and check if it is filled till 5000.
Not in reverse order, in forward order only. Starting from the fifth last location, you have to